Now let's look inside our uniformly charged sphere. So some of this is going to be the same. We still have spherical symmetry, so we still want to use the Gaussian surface of a sphere, but now we're inside our sphere. And so what this means is that the amount of charge that is enclosed in our Gaussian surface depends on the radius that we write. If we were outside the sphere, as we were in the last video, then any radius includes the entire sphere. But now we are inside. So part of your sphere of charge is in your Gaussian surface, and then some of it isn't. Now remember, one of the things we looked at in the previous section was that charges that are outside your surface do not contribute to your flux. So the only thing we have to think about is charge enclosed. Please don't get psyched out from that, and that's one of the reasons that you should actually start from the equation. So our equation, and again, in the previous video, I went through why we really want to start from all three pieces, so go back and look at that if you skipped it. We have our flux is equal to, the definition of flux, is equal to the charge enclosed over in epsilon naught. So again, don't get psyched out by the charge that is not enclosed. It doesn't matter. So your charge enclosed is what's inside your Gaussian sphere, and we need to figure out what that is. So now there's different ways that you might be told about this, but one way to think about it is that it has volumetric or volume charge density. So every little piece of this has some charge, and a certain amount of it falls inside our sphere. So rho is the symbol that we typically use for volumetric charge density, or just charge density. And so in this case, the charge enclosed is going to be what the charge density is multiplied by the volume of our Gaussian sphere, right? So remember that little r here is of our Gaussian sphere. Now, the definition of the charge density is that you have total charge, Q, right? So total charge divided by total volume of the whole sphere. So this V here now corresponds to that. So that's why 4 pi capital R cubed ends up on the bottom. So in some problems, you might be told the total charge of this sphere and its radius, or you might be told its charge density. So recognize that I'm setting it up using charge density and then defining it in terms of the sphere. There might be a shortcut depending on how the problem is phrased, what information you're given. So we know what our charge enclosed is. I'm going to use rho initially, but I'll simplify it down at the end. So now, just as before, this whole surface integral of E dot dA is going to simplify because you know that your electric field is radial in nature. I know that my dA is also pointed that way. So everything is nice and simplify-y. I just get to multiply. So now what I'm doing on the right is saying, okay, my charge enclosed was this, and so I'm putting that over here, over epsilon naught. So I've just rewritten this first equation here and simplified it out. And again, at this point, you're really not using this side anymore. You're really just interested with this. So now we have something about our charge density, the radius of our Gaussian sphere, and we also now need its surface area. Now again, be careful every time you're thinking about the area or the volume. Is it of my charge sphere or my Gaussian sphere? And in this case, Gaussian sphere. That's what you're doing the surface area over, surface integral. So 4 pi r squared is the surface area of your Gaussian sphere, and now all we need to do is rearrange. Now notice that there's going to be a little bit of simplification here, but now what we're going to get is our electric field as a function of radius. So to go a little further in the simplification, the radius here is of, again, the Gaussian sphere, and so that's basically telling me what the electric field is going to be as a function of the distance from the center of the sphere. So you want to simplify this. This is not actually simplified down. But one of the other things we want to do is plug back in rho. Again, in some problems, you might be told what rho is just in general, especially if it's like a slab of charge or a wire of charge. Those you would be told either rho or eta or lambda. But here, let's go back to our primary information, which was the radius and the total charge of our charged sphere. So we're going to redefine this, plug it back in, and now look at this beautiful canceling that is going to happen. We have a 4/3 pi that cancels. This r cubed is going to just become an r to the 1, but cancel that whole thing on the bottom. And so we are left now with an electric field that goes as q over r cubed, but notice that those are constants, right? Those are constants, and then we have r over 4 pi epsilon naught. This is actually quite striking. This tells you that your electric field actually gets stronger as you get further away from the center of the sphere. So there's this really helpful plot. If you're at the very center of the sphere, your electric field is 0. And one of the ways you can think about that is if you're at the very center of the sphere, from symmetry, which way would your electric field point? Because you need to have a rotational symmetry, you need to have a reflection symmetry. So the only way, when you have a whole lot of symmetry at the very center, for that symmetry to be preserved is for it to be 0. Because if, for instance, we said, oh, it points to the right, well, then when you used your reflection symmetry, it wouldn't work. Or if we rotated it, oh, now it looks over there. That's also bad. So that's part of why we could conceptually get to the fact that the electric field at the very center of a charged sphere has to be 0. And now this is a function of the radius you're at. So as you get further and further and further away, it actually gets stronger and stronger and stronger until you're at the very surface, and then it falls off as 1 over r squared. And that's what we found in the previous video. So this is rather lovely that you can't actually get this result easily other than using Gauss's law. And Gauss's law then shows us that the field behaves very differently on the inside versus the outside. Now, one thing I want to point out is that it's quite difficult to show what the electric field of this solid sphere looks like inside using field lines, because as you keep going through the material, you actually have charge everywhere. So you would kind of be adding more and more field lines as you get further out, and it's hard to figure out exactly kind of how to do that. So it's a little difficult to actually show this with field lines. So this plot is actually a really nice way to show it. So again, this is now a plot showing you your electric field strength versus radius. The maximum value is actually right at the surface of the sphere. So hopefully this helps. Again, this is the point of Gauss's law. This would have been next to impossible to calculate with Coulomb's law, but now we can get this nice result with only a few lines of algebra and a lot of reasoning through symmetry.